All right. So,
Uh, I can try to talk from my computer. I don't know, something's up from the speaker of this thing, but I
mm,
can do it now, right? All right. I can try to talk from my computer. Amazing. I don't know, something's right. Up from the speaker of this thing, but I can do it now. Right. Welcome, everyone. Today we had the pleasure to have Professor Stephen Waslander. He is a leading authority on autonomous robotics, including self-driving vehicles and multi-robot drones. He received his bachelor in 1998 from Queen's University, his master's in 2002, and his Ph.D. in 2007, both from Stanford University, Aeronautics in Aeronautics and Astronautics. He was recruited to the University of Waterloo from Stanford in 2008, where he founded and directed the Waterloo Autonomous Vehicles Laboratory, where he led the Autonomoose project, the first self-driving car to be tested on public roads by a Canadian university. In 2018, he joined the University of Toronto Institute of Aerospace Studies and founded the Toronto Robotics and Artificial Intelligence Laboratory Lab. Yeah. With that being said, we're very excited to have today Steven. He's a friend of the lab, and I think he's really the first person that actually gave a talk for the second time in the seminar. So we're very excited to have you today. Please, Steve, take it away.
All right, wonderful. Everyone can hear me all right? We're good. Okay. Today I'm going to talk about reasoning robots and our foray into open world navigation and trying to build a set of robots that can do more flexible and more complex and more varied tasks in the open world. And of course, this has been a long-standing dream, right? We all grew up on this culture of, soon the future will be here and robots will solve all the things we don't want to do. Maybe they'll hunt us, maybe they'll clean for us, maybe they'll process data and fly ships for us. But immensely capable and flexible robots that can think like humans, talk like humans, and work with humans. And so I think we're starting to move in the direction where this is actually now possible. Or maybe the right way to say this is we can take a big step forward in this vision of universal or generalizable robots. We have multiple tools that have come along, right, that really give us a big leg up in this. The first being open world scene understanding, the ability to perceive the environment and decompose it into a set of objects of unlimited extent, right? Essentially, anything we look at, we can apply a label to and be reasonably accurate in that process. We now have similarly massive advances in natural language processing. I'm not telling anyone anything they haven't heard before, but we can include vision as well as language into the inputs for these multimodal language models and start to reason, automatically based on a large history of all of the writing ever included on the internet. And this is just a fundamental change in the way you want to then be able to interact with robots. And finally, the advances in RL and in deep learning have led to major improvements in mobility and manipulation. So our ability to actually execute these maneuvers and these plans are getting increasingly more effective. And that means that we can do many, many more tasks, right, and handle them reliably and autonomously. So for me, this project really started about 2, 3 years ago. Created the Trailbot, which is this little robot here. This is a ClearPath Husky with a large box on it. On top of the box, we put a laptop, we put a LiDAR camera, a microphone, and a speaker. And we hooked it all up to essentially the ChatGPT interface with language processing. And what we ended up with, in the box, we placed a snack dispenser. And so we ended up with this robot that could drive around on hiking trails, find humans, chase them down, essentially, as it's doing here, and then interact with them. So I don't have the audio playing, but essentially, this is Miguel, and he was he talks to the robot. He says, "Hey, the robot asks, would you like some snacks?" to Trailbot, and then he goes, "Yes, I'd love some snacks. What do you have?" It says, "Do you have chips, or would you like chips, chocolate, or crackers?" And then he picks one, and then of course, a few seconds later, the chocolate drops out, and he grabs it, and then the robot heads on its merry way. Right. So this is not research, really. This was a sort of a summer project, gluing together systems that already existed. but it was this proof of concept for me in the lab that, you really can just talk to robots now, and they can actually understand. At one point, I asked the Trailbot how I should tie my shoes. I asked it what its name was. I asked it, a whole variety of different questions, and every time we got some kind of interesting answer, right? This is just, as you all know, interacting with ChatGPT can be quite entertaining. But the idea opened up options for us. And so we started looking at what we could build that would actually become more applicable or more useful in this direction. So today I'm really going to talk about two papers that have emerged out of this Trailbot project. The first being OpenNav, where we try to do open world navigation using agentic reasoning, and that was a IROS 2025 paper. And finally, STAR, which is our most recent work, and I think we just submitted it to TRO. And this is a scalable task conditioned retrieval. So trying to do long horizon multimodal memory in robots and use sort of this history and this storage to resolve more interesting tasks in the warehouse setting primarily. Okay, so let's jump in. So vision language navigation has been around for a while now. The R2R dataset allows you to actually navigate through a 3D world that's reconstructed from recorded data. And so you can actually ask questions, right, provide instructions, and navigate from one location to the next. The robot can either have access to the whole map or it can build one as it's traveling, right? You can do all these kind of things. And over the years, it's been slowly expanded. So 2018 was the first R2R data set. Then R2R CE and our XR CE came out with Google's help with increasing realism, more detail in the environments, and huge numbers of multilingual instructions. So 126,000 different commands that can be tested in this larger environment. This led to foundational works. One that I always liked, the one is sort of, along the same time that we were building the Trailbot, really piqued my interest, was VLFM. So here is you get a language command to saying find an object or find a location in the environment, and you look in various directions and you try to figure out which direction is useful for resolving that command. So for example, looking at the kitchen with the text prompt of bed, you're unlikely to get similarity between the text embeddings and the vision embeddings for that scene. Whereas if you're looking in the direction of a hallway and at the end of the hallway, bed structure or some doorway into a new room, you might have a stronger cosine similarity, right? And that will then lead you to explore the frontier. You're more likely to uncover the object you're trying to search for. So this was a really neat idea, taking that language command and connecting it using the blips and the clips, right? The vision language correlators essentially to try to solve that task. The next paper that got us excited was SGNav. So here, trying to solve that same navigation challenge, this open world navigation challenge on those data sets. One of the big contributions here was this idea of chain of thought reasoning and the use of a 3D scene graph, right? So the scene graph had multiple layers, right? It has rooms, it has objects, etc. And it allows you to sort of reason about environments as you're constructing a map of it and locate objects within their bigger context. So beds are in bedrooms, toilets are in bathrooms, things like that. And all of those words can be helpful in the LLM reasoning in how to resolve a task. And the chain of thought idea, right, forces the language models to decompose the way they think about a problem statement in a specific structure. And that means that you have more repeatable sub-goals essentially in the analysis or in the reasoning. And with those sub-goals getting executed, you get sort of a consistent sequence and are more likely to find, based on this conversation, the true direction in which to travel to identify a goal. So this one was really exciting too, and it increased the success rate on those data sets by another 5%. The last one that helped with formulating OpenNav was the idea of a two-level framework that came out in Navila. And so here, what's happening is that the high-level reasoning agent isn't necessarily that capable at exactly understanding how to execute the maneuvers that are required in the end, right? So you can divide this into two pieces, obviously, and use a low-level visual locomotion policy with, a known set of capabilities, right? Move forward, turn right, these sort of things. And then the high-level agent can basically call that API from the low-level command system and use that policy to actually execute higher-level maneuvers, right? And so this is a really useful idea. This decomposition, of course, exists throughout robotics, and so it's one that we incorporated as well. Okay, so given these inspiring works, what were the challenges we set out to resolve? First off, we wanted to be able to handle open set instructions, right? So with varying or more increasing levels of spatial and semantic reasoning required to understand those instructions. So we wanted to be able to do things like handle similar objects, multiple chairs, multiple vehicles, whatever it is, and be able to distinguish between them based on shape or color or location. We wanted to understand the spatial relationships across large unstructured spaces, and hopefully be able to handle tasks that required that understanding. We wanted to, of course, handle open set objects, so we didn't want to have to work on a subset of objects that were predefined, right? So we want to be able to reason about those objects and also reason about objects that aren't seen. So understand context in the environment and where objects are expected to be located. We wanted to do this two-level, right, ground high-level instructions to low-level control commands. So plan sub-goals and generate control commands. And then finally, we wanted to make sure that we made progress on spatial reasoning, because we know working directly in the LLM space, you end up struggling with that sort of spatial understanding. And so we really wanted to anchor our work in VLMs and make sure that the spatial component was a big piece of it. So we organized a set of tasks on the Kitty benchmark. So basically on the Kitty data set, we constructed 3D worlds from it from various viewpoints, and then generated sets of tasks associated with those views. So the first one was sort of multi-step instruction following: go straight, go into the yard, and when you see a trash bin. So we have two different instructions there, and they require understanding of the objects in the environment. We have spatial reasoning, so go to the house on the right. So where's the right relative to you, right, etc. We have attribute grounding, so please stay right, and then go to the cylindrical building. So we needed it to understand the shape of a cylinder, and use that to identify the correct structure in the environment. And then go to, functional comprehension, right? So please throw some trash away. So we need to understand that a trash can was what we were looking for, find the trash can, and then navigate towards it, right? So all of these tasks were sort of, expanding in their difficulty over what was existing in the state of the art, I guess, about a year ago. But now they're more common. There's other methods that are doing this sort of stuff as well. So the big core piece that was needed in order to do the reasoning part was to have a clear representation of the environment that we could insert into our multimodal language models. And so we built our open vocabulary perception system as follows. We take obviously an input image and the LiDAR point cloud from the Kitty data. We do segmentation, decomposition, labeling in an open world setting. So all of these labels here are instance labels. They have names associated with them for the objects, So they have different descriptions of those objects. And we take that whole decomposition and we can build a 3D reconstructed map that projects those segmented regions into the point cloud, and then comes up with 3D objects for those individual pieces. We take the original image and annotate boundaries on the objects as well as labels, and we provide that annotated image and text as a primary input to our MLLN for reasoning. And we use our 3D reconstructed map to build an occupancy grid map. So I guess I should use my cursor a little bit. So we're over here now. So we build this occupancy grid map, where the different objects are included, and we can convert that into a semantic map as well, where we use the labels generated from our initial segmentation work to create, individual regions that have different, labels or descriptions attributed to them, right? So this is our whole representation of the environment. We're going to feed this component into our MMLM, and then we're going to use the outputs of the MLM to actually modify these downstream components in order to perform our planning. And so this is how the whole system works. So we start from some initial command prompt, right? Please drive towards the black car, then head to the house on your right. So this is the scene that we're going to be looking at. We're located here at the bottom, and we're trying to come up with a plan that goes to this house over here on the right. And we want to head to the car first and then move over from there, right? One of the big pieces we had to spend a lot of time on was our task agnostic prompt. So this is the prompt that basically sets up the mission for the VLM or the MMLM. So it has to describe essentially an API for our robot, all the available functions that can be called, all the capabilities it has. We set up the environment, we define how code can be generated, and we can provide an initial plan even, or how planning should be performed, I should say. So you can use the A-star algorithm on a value map in order to perform planning, et cetera, et cetera. So we have some details like that. So all of this goes into our MMLM along with the outputs from our open vocabulary perception system. And together, right, the reasoning component starts to generate code for us, and it automatically generates this sequence of steps to define a plan to get from our current location and follow the instructions from the initial prompt. And so what actually happens here is we actually iterate a little bit, and we allow the MMLM to actually change the heat map or the value map for planning that was generated from our occupancy grid. So it can, based on the instructions here, right, it can actually say, it can add in different regions where the vehicle is, preferred to go, for example, or regions that it wants to exclude, with a higher penalty. And so the MLM is actually going to modify the way the plan gets generated, but we'll rely on A-star to give us a, consistent plan. So we're using that sort of two-level approach that we're describing there. And that seems to work quite reliably. So let's see how this plays out in a couple of scenarios. We got lots of examples in this work. Obviously, it's a lot of fun to look at the examples. So first one here, we drive straight for 20 meters, right? So we get a plan, right? We've got our environment decomposed, our annotated image with all of the different individual segmented objects in the scene with text associated with them. We've got our occupancy map and our semantic map. Everything's ready to go. We turn this semantic map into a cost map, and we plan with A-star. And of course, go straight is relatively easy, so we get a perfectly straight trajectory out of this. And all the different methods that we compare to agree that this is the right way to go from point A to point B to go straight for 20 meters. If we modify the prompt, we get drive straight for 20 meters, but avoiding the area with white text on the ground. This requires the VLM to understand that this is white text, that it's on the ground, and that it's located in an area in our value map. And so you can see it inserts this large high-cost region right there over the numbers 30, the speed limit, right, that's painted on the ground. And then once that heat map has been modified, all of the trajectories then change in order to solve, right? So our VLM method goes around the outside, the A-star goes around the outside, and only the original plan runs straight down the middle. And then finally, if we modify it one more time, drive straight for 20 meters, avoiding both the area with white text on the ground and the shadowed area on the ground. This large shadowed area was labeled, right? And so it's going to avoid that as well. And so it adds another high cost region here and then chooses to navigate around the outside, right? And so that's the idea there. Wonderful. Okay, so everything seems to be working as expected. We see these MMLM generated modifications to our heat map, and we see the resulting plans are consistent with that. So here's some more examples. So first, go to the black fence straight ahead and under the shadow while maintaining a safe distance, and then from there move towards the tall tree. So this requires multi-step reasoning, and we can see that the path generated does exactly that. It moves into the shadow first near the black fence and then travels along the sidewalk to the tree. Similarly, right, drive straight first, then steer towards the card with a blue image on the door. So here's the blue image on the door. This requires it to reason about which of the vehicles is the one that we're interested in. And so identifying these visual features at the same time as the spatial location, and then navigates a plan towards that. And finally, go to the car on your right that is farthest away. So this requires reasoning about the spatial location of different vehicles, right? So here's a car that's farther away on the right, and this is the car that's closer that's on the right, so it has to ignore that car that's nearby and move to the correct one beyond it, right? And all of these things are working relatively reliably. So wonderful. So we built a fairly large set of examples. In this case, I think it was 50 different questions, different tasks in those 4 different categories. We compared to state of the art and showed that we could outperform. We also compared to some simpler baselines relative to OpenNav and an ablation, right? So we could plan directly with A-star off the original heat map, or we could apply just directly use the vision language model to generate code. And what we see is when we use the 2-stage approach with the VLM modifying the heat map and then doing planning on top of that, we get significantly better performance across, right? And so in A-star alone, we have no collisions. Obviously, when we just ask the VLT to do the code, we run up with significant more collisions, and then OpenNav recovers most of the performance there, which looks great. So we're very, very happy with this. Okay, so let's do just a couple more quick examples. I don't want to take too long because the other one is also a lot of fun. But let me show you, we implemented this on our Trailbot. And so here we have a live demo. There's Mingfeng sitting at a desk there. And the instruction is take coffee to the person using the computer, right? So it needs to understand what a computer is, where the person is relative to that, and then start planning a route. And sure enough, it's able to do this in this nice, simple environment, right? So there's lots of clutter, there's lots of things going on in the scene, but the reasoning makes sense, right? And it finds the appropriate plan to the correct location in the environment. So here's a couple others. Whoops, let's see. Oh, I think I've jumped quite a bit. What's happening? Oh yeah, navigable car. So this is a nice example. We have a car on a poster, and we have a car in the real world, right? And we use the word real to differentiate between the two in our instruction. And sure enough, it's able to navigate past the car because the picture is labeled as an image of a car, right? Or a poster with an image of a car. And so we're able to differentiate between those and find our way through. So there's some ambiguity in this scene as to which object we're considering. And there goes our little Trailbot right on its way over to the correct object. Very nice. Okay. We did this outside as well. So what sort of navigates away. And we can see some of the plans. So the task here was to avoid the sign on the ground and find an object that we could use to block a path. So help find something that can be used to block the path, but don't step on anything you shouldn't step on, right? So some good ambiguous human instructions right there. And sure enough, it sees the sign, navigates around it, and then moves over to the construction barrel as a way to block, right? Wonderful. Oh, avoid the grass in this one, right? So I'll jump forward. All right, wonderful. So what was nice about that first work really was that it opened up the door to open world navigation. You could see we were really still relying only on information that was visible within a single frame, right? So we were doing segmentation on the image and using the point cloud for one scene and not building maps or any kind of history. And so for the next step, we really wanted to expand to, more realistic operating environments. And so the idea was to try to incorporate some sort of structured memory. And of course, there's many wonderful works in this area. I have to start with this one, of course, for this crowd. So I distinctly remember visiting Montreal in 2023 for a rather infamous CRV conference. But I met up with Liam Paul there. And the two of us had this fascinating conversation where I was talking about some of the work I'd been doing on object-oriented SLAM, and he told me about concept graphs. And the level at which he was talking had nothing to do with what I was talking about, and it took me a long time to realize how cool this project was. But it's become a seminal work for us, really one that inspires us, and it's this idea that you can decompose the world and construct a graph, conceptually, and use this sort of graph representation as a structure for how to navigate around environments and how to resolve tasks that are object specific. So I really like that. OpenGraph expanded on this idea for outdoor environments, and so this is actually the code that we're using, right? So it worked on hierarchical scene graphs, very similar category to concept graphs, right? So rich semantics, but overall quite slow. And what we're doing really is this, right? We use an RGB image. You apply recognize anything to generate a bunch of labels as to what's visible in the scene. You feed those into a grounding dyno model in order to get bounding boxes on all of the labels that you've just generated from that same image. And then you pass it to tokenize anything via prompting, and you end up with the combination of segmented regions in the scene and labels on top of it, right? So this massive pipeline of 3 giant foundation models was the way forward in the OpenGraph paper. As of yesterday, I think we have SAM3, which can basically do all of this in one shot, right? And so maybe there's an easier way forward for future steps. So really a fascinating sequence, but what we get is that same view that we had in the OpenNav paper, right? This idea that the entire scene in front of you, and in fact, the entire map as you're building it, can be retained and stored as a graph representation, and every object you observe can have a label associated with it that's useful and descriptive of what that object or region is, right? This becomes overwhelming fairly quickly as you start to scale up to large environments, right? You can have a massive scene graph. You can have redundancy and over-segmented objects. There's a question about resolution. How detailed do you want to decompose things? Do you want to know about every pen in a pen holder, or do you just care about larger objects on the table? And Clio came along and tried to address this to some extent, right? So this is Luca Carlone. And what they're looking at here was a way to revisit the generation of the scene graph based on the task that's required. So passing information through a bottleneck, and only retaining or structuring your scene graph based on semantically relevant clusters or regions in the environment that are of use. Another paper that got us really excited was this idea of Remember, right, which actually tried to incorporate long-term memory, and tried to record what had happened in an environment over a sequence of time, without necessarily retaining all of the sensor data. And so this was a really interesting idea for us because it allows you to essentially use a video captioner to process subsets of your sensor data, and store just the captions as a description of what happened in that set of or that time interval, essentially. And these captions are obviously much more compact than the visual or video data, and therefore can be queried at a subsequent time and can be used to resolve tasks that have some temporal component to them, right? And similarly, to identify actions or events that happened that might be of interest to solving problems. And so Remember was actually one of the early works that applied themselves to this NAV QA dataset, which came up with different types of tasks of different lengths. So long history, medium history, short history in both spatial, descriptive, and temporal categories. And so there's sort of a query phase, right? Trying to come up with an answer given a long video sequence, and trying to understand, navigation questions related to, and historical questions or temporal questions related to what's happened in a video sequence. So we wanted to take these ideas and basically move our OpenNav capabilities to some longer term, larger scale environment, right? And so one of the big things we needed was some way to build a memory, right, or construct a representation of the world that could solve a bunch of different kinds of tasks over a longer period and over a larger scale. So we need this ability to retrieve information based on the task that we've been requested. So we don't want to look at everything. we want to store the information in some way that's representative, and finally, we want to reason across the different modes and the different ways in which we're going to store information. Right? So all of these challenges we tried to put together into our STAR paper. And so the big piece was really how we structured our memory. So here's what we did. We started from our standard open world perception system and constructed a large-scale 3D scene graph. Right, so that's sort of this piece right here. This is our large warehouse environment we build in IsaacSim. And so all of the shelves and many of the boxes and all of the forklifts and tools and whatnot are captured within some large-scale scene graph, right? So this gives us really a strong geometric representation of the environment and an ability to reason over the individual objects that are in that environment, but it tells us nothing of the history and is at some sort of fixed granularity, essentially, right? We then simultaneously take all of the input data that was collected in order to construct the scene graph, and we divide it up into video segments, and each video segment gets a caption associated with it, and that gets stored in some caption database, right? And then finally, at sort of fixed intervals and where interesting things were visible, we extract a set of keyframes, and these are essentially the raw sensor data, but stored at sort of a sparser scale than it's actually being captured at on the robot. And we can use these to sort of refine or resolve questions when we know when to look at in time, right? And we know what we're interested in from the geometric perspective, but we don't exactly know how to resolve the answer completely. And so this gives us essentially a geometric, a temporal, and a detailed visual representation of the environment throughout the history of operation. And that's really what we got excited about. So those three pieces together give us the ability to start answering some really interesting questions. So let's look what we could do to actually use this, right? So first off, let's try to come up with a set of new queries that are more challenging. So please place this box on the shelf where it belongs. Right? So what does that mean exactly? Well, we're going to be provided a box, right? It's got some information on it, some sort of label, and we're going to look throughout our entire history of where similar boxes were placed, and we're going to try to find the right solution, right? The right location for the box to be handed off, right? So we'll take this kind of user query, right? We'll have our standard agentic planner, right? The MMLM. It's going to basically take everything we need in terms of the query, retrieve the necessary memories, pass the memories through an information bottleneck to only use the relevant information. If we have enough context to solve the problem, we go into memory and generate the contextual reasoning in order to perform or answer the task. And if we don't, we can go back and do additional queries into memory, right, and try to identify those pieces that we need in order to help resolve the situation. So for this, place the box on the shelf where it belongs, right? The user's referring to a box that had the word fragile on it. We've seen fragile boxes on several shelves in the warehouse. And so once we figure out which of those shelves that have fragile boxes has an empty slot, we'll find that and then we'll navigate to that shelf. And all of this is organic, right? All of this reasoning about where to put this box is being generated by the MMLM directly from this single prompt without any kind of, user input or preconditioned prompt, right? That actually tells it how to think about this problem. So really fascinating what kind of detail we can get to. And so we'll evaluate this on the two settings. So the NavQA benchmark, which is this existing one that I was just describing, as well as on our warehouse where we generated our own set of interesting questions. And we have this full simulated environment that we can operate in, which is really pretty exciting. Okay, so this is a pretty dense slide, but this is the core idea of the paper. So we'll sort of walk through a sequence here and try to describe all of the pieces. So the first up, here's 4 different tasks. Each one's slightly different from the other, but they're all sort of relevant to each other. So, task 1 is locate the white digital twin boxes in the staging area. The second one is to locate the beige digital twin boxes in the staging area. The third one is which shelf should this white digital twin box be placed on? And the fourth one is how many free pallet slots on the shelf with the white digital twin boxes, right? So the first 2 are find the things in the staging area. The second one is where should I put it? And the last one is there any space, right? So these are all possible questions that we can ask about a very specific set of boxes. It's actually these little ones right here that have this word digital twin sort of on the side. You can see the logo down here. Here's the digital twin on the side right there. Yep. Wonderful. Okay. So our task conditioning regioning, right, is going to work as follows. It's going to find keywords in the instruction. So white boxes, digital twin boxes, and then it's going to invoke the APIs calls in order to start solving this. And so the first thing it does is it generates keyword embeddings, and then it retrieves task relevant video captions with timestamps from our vector database, right? And so it's basically going through our whole history of captions, and it's identifying those specific memories that have something to do with these keywords, right? And so here we can see kind of this subset of captions that have been selected, right? And each of those captions has associated with it a keyframe, right? That's sort of displayed up there. And all of those captions are then going to start, being used to identify how we should solve this problem, right? So this task conditioned 3D primitive set, right, expands the whole history of memory, and we get these sort of different clumps and different clusters where these objects that might be relevant to our task are actually located. And so what we can now do is we can group these for those that are above some threshold, and we can now go into our geometric representation, our hierarchical scene graph, and we can actually apply the information bottleneck idea from Clio and find those subsets of objects in the scene graph that are actually relevant to these clusters of captions, right? So since this is a robot moving through the environment, we usually have captions clustered together related to a specific set of objects that are actually relevant. So we have, here we have the boxes in the staging area, the two different colors, right, with those same logos. Here we have boxes on a shelf, which might be a good place to store it. And so we need to actually start reasoning about these different clusters, but we can ignore everything else in the scene in order to perform this operation. Okay, I better keep moving. And so ultimately what we end up with is we end up with these 4 different clusters, right? Each one we can retrieve a keyframe for, and we can inspect those keyframes and try to resolve the final elements of these questions, right? So the white boxes in the staging area, this is the staging area. As labeled in the hierarchical scene graph, there's the dynamic digital twin logo. And so, this solves question number 1. Here's the beige box with digital twin, solves question number 2. Here's the fragile box. This one doesn't help us with 3. This is an irrelevant area. And here we have digital twin boxes with an area that we can store the palettes in, right? And so ultimately we get all of these answers coming out from the overall pipeline. Wonderful. So here's an example of it working on the NAV VQA data set. It's where the task is to where is the nearest police call pole. And so we look through our history of navigating around this environment. We see multiple instances where the different poles are located. And what we found relative to Remember, because we have this information bottleneck, we cluster the captions and identify different regions where different poles were observed, whereas Remember doesn't have that bottlenecking idea and therefore just finds the most common one and therefore focuses in on just a single solution, but it turns out that that's not necessarily the closest one. And so ours is outperforming in this scenario. Here's another example, right, with the which shelf should this be placed on? So again, here's our caption sequence. Here's the ones that exceed some threshold. And then we can select through the information bottleneck ones that actually matter to us. And the cluster-wise grouping gives us, multiple possibilities to explore and reason about in order to solve the task. And so ultimately, we end up finding the shelving area where there's space next to existing digital twin boxes. Okay. So let's show a few examples in the simulator, of course. So this is a warehouse scene. We're navigating around the environment, and this is just sort of building the whole graph. Right, so we're just navigating around, exploring the environment, and we can basically reconstruct the warehouse as follows. Right, so all of this is done in Isaac Sim. It takes a little while. That was clearly sped up, but it's running close enough that we can, consider ourselves funny. So let's try a task. So this is a really interesting one. This is find a bottle with the EQP label. These are small bottles. So in our original scene graph, we don't have these bottles individually as objects, but we have a cluster where a bunch of bottles are being stored. And so the reasoning needs to understand that it needs to look for smaller objects within an area where those objects are present, and then it needs to go back to the keyframes and identify which of the bottles it is we're looking for. And so it actually then has to process the text on the bottles, right, and identify that bottle as the candidate. And it's been around the environment multiple times, so it has different these different objects, and ultimately what we see is we see it navigate correctly to that location where all the bottles are. Here's another example. The light on the warehouse roof is broken. Please find a suitable ladder. So it looks around the environment for objects that might be considered ladders, right? It passes that through the information bottleneck and only has these subsets that it needs to explore. And then it selects the nearest one. And sure enough, there's a ladder in the corner that you could use to fix a light bulb, right? So fascinating. Yeah, we built this whole GUI just to make it a little easier for Professor Waslander to understand what the heck was going on. And it's been really, really useful for debugging as well. Looking at command prompts, spitting out text from a VLM is not my favorite way to understand the process, but it was really fun. Nicer examples. Okay, so here's another one. Please go to the staging area and find a box identical to this one, right? So it needs to understand both the box it's looking at and then find matching boxes. It needs to know the structure of the environment, and it resolves all of these reliably. So we're getting really excited about this because this really starts to feel like these might be tasks that you might actually ask a robot to go do for you in a warehouse, right? It really becomes high-level commands that you can start to demonstrate. And of course, what we're missing is any ability to affect the environment. We're just looking at things right now with our navigation robots, but that's for us. So I've got a few more things I wanted to mention, and then I'll open it up for questions. So when you look at what's going on in the evaluation, both the NavQA and the warehouse VQA tasks are separated by different categories, right? Spatial, temporal, and descriptive. So this is the NavQA decomposition, and you can see, right, there's an interesting mix of long, medium, and short tasks, and their type is quite different, right? So spatial tasks is where is something? Can you take me to the right place? Temporal is how long were you here? Did you see something previously, right? And descriptive is was the sidewalk busy, or what color were the couches in the atrium? So things that describe the objects. And so all of these are included in this challenge. So our results are exciting. We've got tables where we're doing better than everybody, and by a significant margin. So our success rates on the NavQA benchmark are strong. The temporal tasks turn out to be relatively easy for everyone. So Open Graph and Remember also solve all of the temporal tasks, but on the harder spatial and text or descriptive tasks, we're doing better, which is really exciting. And then we tried to really push the boundary with our warehouse tasks and make them significantly harder. And you can see a major drop in performance across everyone, and some of the largest gains from our methods, obviously, right? This is always what happens when you build your own data set and evaluation benchmark. You can usually make your own method work the best, right? But we're hoping to release this relatively soon and have people experiment on these challenges as well. And we're excited because, we're getting to 67% success rates, but really, there's still room for improvement. We've made tasks that are still too hard for us. And in the memory representation, in our ability to decompose the scene and sort of resolve these longer term tasks. So we're optimistic that there's more room for improvement in the challenges we've already generated. Wonderful. Okay. So those are the big points I wanted to make. I feel like I talk really fast on Zoom, so I apologize. But if there's any questions, I'm happy to take them. STAR is a agentic RAG, essentially, for robots. It's storing everything it observes while it's constructing its environment, and it uses all of that information in an efficient way to perform reasoning. It's scalable, it's multimodal, right? It's robust in these sort of open world settings. And we're really looking to do a lot of interesting stuff with this now that we have these longer term memories. We'd like to see if we can get higher on our success rates on the existing challenges, obviously, and improve overall on grounding of the subtasks in the long-term memory. And for the project as a whole, beyond STAR, I think really what's going to get exciting is when we start moving into dynamic scenes, where there's human operators and forklifts and things moving. I think it's going to be really nice if we can start interacting more tightly with humans, so understand errors that we're making, plan revisions, asking for clarifications when we don't know what to do, understanding human gestures, and then finally actually moving objects in the scene, adding in a manipulation component, looking for collaborators. It'd be really fun to add that into this whole pipeline as well. And so with that, I'll open it up to questions, and thanks for your attention. Awesome. All I hear is silence. All I hear is silence. Okay, so let me know how you want to do questions. Yeah.
I have a question. I was wondering if you could talk a little bit about some of the main failure modes you guys were seeing with your method.
Yeah, so what we tend to see in terms of failure modes, we got a bit of an echo. I'm not sure if we can do anything about that. Okay, great. Yeah, so what we see in terms of failure modes is a lot along the granularity of the objects that are available, right? So if we ask a task about something and it's not able to find the specific object that we're interested in, that's one failure we see. We see sort of confusion over similar objects, so moving to the wrong location, because objects have a lot of similarity in either their appearance or their use. We see some confusion on the recall from the video captions. So some of the video captions don't necessarily describe everything that's happened or all of the things that are relevant to the tasks. So there's just some blanket misses in terms of the recall in that area. It's sort of what you would expect, right? Like a lot of the quality or the precision with which we decompose and understand the scene is still a bit of a problem, and the multi-step reasoning doesn't always generate the same consistent sequence of actions that actually solve the task. So we end up getting stuck partway through a task sometimes. Yeah.
Interesting. Thank you.
I see. Great talk. Thank you.
Great. Thank you.
I have a couple of questions, just to be precise. So in your rack memory, are you also storing like image frames, or is just like text captioning that you are saving over there?
Yeah, so the memory has the three components, right? It has the full hierarchical scene graph. Here we are. It has the caption database, right? So the captions, the time at which they were taken, and the position at which they cover. And then we store this visual database of keyframes associated with the captions, essentially, right? So sometimes we sample, I think, a bit more frequently than we take captions, because the captions cover some window. But we have at least one visual keyframe associated with each caption.
Understood. Right. And also, this is just out of my curiosity. I work on all this area where I advocate for the fact that like you want your representation to have some notion of predictive capabilities, where you just don't go through to the object where you believe it was, but where it will likely be in the future, because you will likely have like an outdated state of your work. But this is something that is not that popular, I feel, but I would like to have like your thoughts now that you are working on this area, and I know you also have a bunch of work in dynamic, SLAM, and related fields.
Absolutely. That's a really nice idea. We have not done any sort of prediction for movement of objects, right? We're very much still working in a static environment. The history, right, is not one that actually tracks objects and their changes. The dynamics, the scene graph is still very much static. So that hasn't entered our work at all, but it's a fascinating idea. And certainly as we start talking about dynamic objects and actors in the scene as part of the overall representation, right, will not only want to record what they did, but will also want to be guessing or estimating what's going to happen in the future. You know, as always, it requires some sort of predictive model, some kind of, you know, either large data set that tells us how these objects will behave, or some, you know, model of the dynamics or the actions that are being taken in the scene. So I haven't really applied any of that yet, but it's an interesting concept. In a warehouse setting, I think it's not as relevant, right? Objects are either where they are, or they're currently being used to do something else. But really, it connects with the idea of change detection as well, right? So the need to update the maps with new information and remove artifacts that exist from previous scans that are no longer relevant, right? So that whole updating that we've talked about in the past as well. Yeah.
Thanks, Steve.
For sure.
Does it work?
Yeah, I will not mute this one. So if you want to make questions, go ahead.
Sure. Can you hear me okay, Steve?
Not too bad. Yeah. Hi.
Okay, hi. So I think the part that I was struggling to understand was actually how these APIs are getting called and how you're deciding like under which situations you're going to call which API. Like I think you gave one example where you actually had to look at the information that was in the visual database because it was like not clear. But this whole thing, if I understand correctly, is like all kind of seamlessly automated somehow through the query response.
Yep, exactly right.
How exactly?
Yeah, so as part of our task agnostic prompt, we tell the MLM how to generate code, right? So there's like code generation prompts and that describe the whole API and tell it what format we'd like the output in. And then we literally get an output from the MLM that does that. And that affects our value map, and it affects our planning, and it runs through this sequence, you know, asking for details, you know, however it needs. So we literally just take the output from the MLM and run it as code, and it seems to work, which is kind of blowing my mind. Yep.
That's insane. That seems kind of insane.
It does seem insane. Yes, yes. And yet that's what's happening. Isn't that cool? Yeah, I mean, it's fairly structured, right? And it's a fairly limited API. So the number of things it can screw up is pretty small. And all of the inputs and outputs are essentially fixed from the rest of the pipeline, right? So you know, obviously we're not getting 100% success rate. I'd have to check with my postdoc to see if the code generation piece is part of the problem, like if the reasoning is correct but the code is incorrect, and see how many times that happens. But he hasn't brought that up as an issue, so it's an interesting question. I'll have to take that back to him.
But so then once you've got this code API, the way that the functions are called is also completely just governed by the MLLM model.
Yep.
As well.
Yeah, exactly. Yep. Yeah. Shocking, eh? Yeah. Yeah. Robots writing their own code to run themselves. It's kind of scary.
Yeah.
Yeah. Is this the singularity? No, can't be it.
It's very cool, man. The star paper, is that available somewhere? I can't find it on
Not yet.
internet.
So for review, and it'll probably go up on archive relatively soon. So we're just polishing the last pieces before we put it up, I think. Yep. So stay tuned.
Amazing. Anybody else in the room or Zoom?
We should be respectful of time.
Yeah, that's
sure
true.
Steve's got things to do.
All right. Thanks a lot, Steve. It was a pleasure to have you, and really, really fun talk. I really enjoyed it personally.
Wonderful. Yeah, thanks for inviting me again. I really appreciate it.
Tell Steve that this was a historic event.
Yeah, I barely mentioned that during the beginning, like first speaker that comes twice to the seminar.
Speaker.
Yeah,
first person
That's pretty awesome. That's pretty awesome.
Yeah.
I'm gonna make myself a badge. Awesome. All right.
All right.
Thanks, everyone.
Thank you very much.
Yeah. All the best.
Ciao.
You.